organizing the event and for providing support for all participants. Second, it's my duty and my privilege to mention that I represent DIMAP, the Center for Discrete Mathematics and its applications at the University of Warwick. And thirdly, I didn't put any the names of my co-authors simply because this talk is not based on any particular result or any specific paper, but I will mention some names below the talk. So here is my story. And let me start with a quick review of the notion of hereditary graph classes. And we all know very well that a class of graphs is hereditary if it is closed under taking induced subgraphs. Hereditary classes can be characterized in terms of minimal for the induced subgraphs. And two classes of particular interest in my talk are bipartite graphs and split graphs. Now let's move to the first notion announced in the title of the talk, the speed of hereditary properties of graphs, which is simply the number of n-vertex labeled graphs in a hereditary class studied as a function of n. And it is known that the rates of the growth of this function are far from being arbitrary. They constitute discrete layers, and the first four lower layers have been characterized by Scheinerman and Zipper. This is the picture of Scheinerman. I couldn't find the picture of Jennifer Zipper. And these are constant, polynomial, exponential, and the factorial layer. Some similar results have been obtained by Alexeyev, my colleague from Russia, who did it a few years later, and who also provided the first three layers with the complete structural characterization. He found all minimal classes in all four lower layers. Some more involved results in this direction have been obtained by Balabash and Langridge. This paper, The Speed of Hereditary Properties, and in particular they found an interesting structural characterization for the bottom part of the factorial layer with speeds up to the Bell number. And from this characterization it follows in particular that all classes in this area are simple, all of them have bounded clique-width. But unfortunately very little can be said, or very little is known about the factorial layer in general, which is a pity because lots of interesting and important classes of graphs belong to this layer, such as interval graphs, permutation graphs, line graphs, threshold graphs, cographs, forests, planar graphs, and even more generally, all proper minor closed graph classes are here. All classes of graphs of bounded vertex degree, etc., etc., etc. So it would be quite interesting to find a common structural characterization for classes in this layer, but this must be a very difficult task. So we propose to simplify this task. We propose a conjecture which says that a class X of graphs is factorial if and only if the fastest of the following three classes is factorial: bipartite graphs in X, co-bipartite graphs in X, or split graphs in X. To justify this conjecture, let me, which is here now, let me mention that if in this conjecture we replace the word factorial by any of the three lower layers, then this becomes a valid statement. We also verified this conjecture for classes of graphs defined by small forbidden induced subgraphs. In particular, we proved this conjecture for classes of graphs defined by forbidden induced subgraphs with at most 4 vertices. We did it with two of my PhD students, Colin Mehill and Viktor Zamarayev. And one of the most difficult cases in this study was the class of claw and square free graphs. Fortunately, Marie Chudnovsky and Paul Seymour found a very interesting characterization, structural characterization of closed-free graphs, which allowed us to solve the conjecture for this case as well. Now let me get back to the conjecture and tell you that the fact that it works for lower layers is based on the fact that in the first 4 lower layers, all minimal classes are subclasses of bipartite, quark-bipartite, and split graphs. And if we knew minimal superfactorial classes, then proving or disproving this conjecture would be an easy task. But unfortunately, none of such classes is known, and perhaps none of such classes exist. To better explain this phenomenon, let me consider some smallest superfactorial classes of bipartite graphs. And one of them is the class of C4 free bipartite graphs, which is known to be superfactorial. Moreover, if we additionally to C4 exclude C6, this class is still superfactorial. And even more generally, if we exclude any finite collection of cycles, then the resulting class is still superfactorial, which follows in particular from the results obtained by Lazebnik, Ustimenko, and Walder. This is Lazebnik, this is Walder. Again, I couldn't find a picture of Ustimenko. So we have an infinite sequence, an infinite decreasing sequence of graph classes. Each class in this sequence is superfactorial, but the limit class of the sequence, the class to which the sequence converges, which is the class of graphs without cycles, is factorial. This is the class of forests. It is factorial. One more interesting superfactorial class of bipartite graphs is the class of chordal bipartite graphs. It was proved by Jeremy Spinrad in 1995 that this class is superfactorial. And for a long time I believe that this is one of the minimal superfactorial classes of bipartite graphs, but recently again with some of my PhD students we found that we can additionally exclude a couple of more graphs without falling to the factorial layer. And whether this new class is minimal or not, we don't yet know. I will return to these 2 classes, chordal bipartite graphs and C4 free bipartite graphs a bit later. Now let me move to one more notion announced in the title of my talk, the notion of clique-width. And to this end I resumed the list of factorial classes of graphs, and I purposely omitted from this list one line, the last line, which says that all graphs of bounded clique-width are at most factorial, which was proved jointly with Peter Allen here and Michael Rao. The next notion in the title of my talk is the notion of well-quasi-order, or if we deal with partial orders, it is known as well-partial order or partial well-order. For graphs, finite simple graphs, this notion can be defined in the following way. Partial order graphs is a well-partial order if it contains no infinite antichains, meaning no infinite sets of graphs pairwise incomparable with respect to the order. There are many different partial orders studied in the literature, such as induced subgraph relation, subgraph, minor relation, induced minor relation, vertex minor relation. And minor relation plays an important role in this topic because, as we all know very well, according to the celebrated result of Robertson and Seymour, the minor relation is a well-quasi-ordered. There are no infinite antichain of minors, which is not the case for induced subgraph, subgraph, or induced minor relation. I don't know, to the best of my knowledge, the question of well-quasi-orderability of vertex minor relation is still open. The fact that induced subgraph relation and subgraph relation, these are not well-quasi-orders, can be easily seen with the example of cycles. Clearly, no cycle can be obtained from any other cycle by deletion of vertices or edges, which means that a set of cycles creates an infinite antichain with respect to both of these relations. One more important infinite antichain with respect to both relations is the set of so-called H-graphs. Again, it's easy to see that none of these graphs can be obtained from another by vertex or edge deletions. And in a sense, these are the only two infinite antichains when we speak about subgraph relation. More formally, Lozin proved almost 20 years ago that a class of graphs closed under taken subgraphs is well-quasi-ordered by the subgraph relation if and only if it contains finitely many cycles and finitely many H-graphs. Vadim is now professor of mathematics at LSU. The situation with induced subgraph relation is much more complicated and less explored. And here is a list of some papers on this topic. And this list is nearly complete. I could possibly add a couple of more papers, but not more. And the last two papers in this list have been written together jointly with one of my PhD students, Nicholas Korpilainen. And while working on this topic, we noticed just by chance that every hereditary class of graphs, which is well-quasi-ordered by the induced subgraph relation, is of bounded clique-width, which naturally leads to the following question, or conjecture if you want. Does well-quasi-orderability imply bounded clique-width? And we are not alone who came to this idea. This conjecture was formally stated recently by Davigo, Rao, and Tomasa in this paper. But again, this must be very difficult. Proving or disproving this conjecture must be very, very difficult because our knowledge in this area is still very limited. So in order to simplify our life, I propose to relax this question in the following way. So we know that graphs of bounded clique-width are at most factorial. And we believe that well-quasi-ordered classes of graphs have bounded clique-width. So now let me replace this question by the question whether every well-quasi-ordered hereditary class is at most factorial. And again, still a difficult question. So we decided first of all to look at two smallest non-trivial cases, two smallest non-trivial classes: chordal bipartite graphs and C4-free bipartite graphs. Both of them are superfactorial, both of them are not well-quasi-ordered with respect to the induced subgraph relation. But we proved that in any hereditary subclass of any one of them, which is well-quasi-ordered by the induced subgraph relation, these classes are at most factorial. Even more generally, we proved that for any forest F, the class of F3 chordal bipartite graphs or FC4-free bipartite graphs are at most factorial. And this easily implies that every subclass of chordal bipartite graphs or C4-free bipartite graphs, which is well-quasi-ordered by the induced subgraph relation, is at most factorial. Because if a class of graphs is well-quasi-ordered, it does not contain any infinite antichain. In particular, it doesn't contain the antichain of H graphs. Every H graph is a tree, so by forbidding any tree, we immediately fall into the factorial layer. I believe I have 10 minutes, right? Including questions, right? So the proof of this theorem in the case of chordal bipartite graphs is more interesting, so let me sketch it. So assume we are given a graph G, a bipartite graph given together with a bipartition. And the bipartite adjacency matrix is a binary matrix whose rows correspond to one part of the graph, columns correspond to the other part of the graph. And in a binary matrix, a gamma is a pair of rows and columns that induce the following submatrix. This looks like a gamma. And it is known that a bipartite graph is chordal bipartite if and only if its bipartite adjacency matrix has a gamma-3 ordering in a permutation of its rows and columns, which is gamma-3. Now, in a gamma-3 matrix, we call a one-entry redundant if replacing it with 0 results in a gamma. So the idea of this notion is that we don't need to remember redundant ones, because to describe chordal bipartite graphs, all we need to know is the set of non-redundant ones. And what we proved is that for any forest F, the number of non-redundant ones in a chordal bipartite F3 graph with n vertices is at most big O of n. And here is a sketch of the proof. So without loss of generality, we assume that we forbid a tree of particular type in which every non-leaf vertex has exactly t children and every leaf vertex is of distance d from the root, because any forest is an induced subgraph of a tree of this form for some specific value of t. So we define A of 1 be the set of the first d non-redundant ones taken from each row. We define B1 be the set of the first d non-redundant ones taken from each column, which are not in A1. And inductively we define AI to be the set of the first d non-redundant ones taken from each row, which do not belong to any of the previously constructed sets. And similarly, we define BI in a similar way. And the idea of the proof is to show that A of d plus 1 is empty. So we assume by contradiction that there is a non-redundant one belonging to A of d plus 1, which implies by definition that this column must contain d non-redundant ones in the set BD. Similarly, for each of these non-redundant ones, there must be a set of d non-redundant ones in each of the respective rows belonging to AD. And moreover, we claim that these ones must be column disjoint, because if this and these ones would belong to the same column, then together with this one and this one, this would make this one redundant. So these are column disjoint, meaning that the graph formed by these entries of the matrix is a tree, and proceeding inductively we conclude that this tree is exactly the tree which we forbid, which is impossible. So we conclude that the number of non-redundant ones is at most 2dn, which means that every chordal bipartite graph can be represented with n logarithm bits, which means by definition, by the way, I probably forgot to give a definition for the factorial layer, but anyway, it's by definition now we conclude that the class of F3 chordal bipartite graphs is at most factorial. Now, having proved these results for chordal bipartite graphs, the relaxed version of the conjecture for chordal bipartite graphs and C4-free bipartite graphs, it's now natural to ask whether the stronger version of the conjecture is valid in these two special cases. So far, we have been able to prove it only in the case of C4-free bipartite graphs, and only in the case of subclasses of C4-free bipartite graphs defined by finitely many additional abstractions. In which case, we must forbid a path, a reduced path, because we cannot kill the infinite set of cycles by finitely many forbidden graphs without forbidding a path. So we prove the conjecture for finitely many forbidden graphs. And actually we proved something which is most strong, we proved that for every k, the class of pk and C4 free bipartite graphs is well-quasi-ordered and is of bounded clique-width. And even more generally, we proved that for every k, n, and p, the class of pk, kn, kpp free bipartite graphs is well-quasi-ordered and is of bounded clique-width. So this is just a special case of this more general result for n equal 3 and p equal 2. And the proof of this result is based on an interesting Ramsey type.
So is it for bipartite graph or the first one?
The first one, no, but it's in general. And again, this theorem actually is based on an interesting Ramsey type result, which says that every graph containing a long path, not necessarily induced, contains either a big clique or a big induced by clique or a long induced path. Which means that if we forbid an induced path, a clique, and a by clique, then we fall. Then our graphs do not contain long paths. Long paths, not necessarily induced. And for graphs without long paths, not necessarily induced, it's known that such graphs are well-quasi-ordered, which follows from Dean's result, and these classes are well-quasi-ordered. So this is nearly it. I just want to mention that you may have noticed that I started my talk by quoting the Beatles. I would like to finish it by quoting one more great singer and composer, Sting. Be yourself, no matter what they say. Thank you very much.